Let's begin our discussion on momentum methods. And in order to do that, we're going to have to define momentum. I'll use the letter L for momentum. You can see it's a vector quantity, and it's equal to mass times velocity. In physics, we'll use the lowercase p for momentum, but here in engineering, we're using an L. So a couple of interesting relationships between momentum and some other things we've already discussed, especially force, can be seen right here. This first line is Newton's second law. In its purest form, force is equal to the derivative of momentum with respect to time. Now generally that has been written in the past as force equals mass times acceleration, but you can see what's happening. Momentum is mass times velocity, so when I take the derivative with respect to time, I have to use the product rule. So that's going to involve the derivative of the first, which is the derivative of mass with respect to time, times velocity, the second, plus the first, mass, times the derivative of velocity with respect to time, which is v dot. That's the same, though, as mass times acceleration. This single term right here, that's mass times acceleration. This term, the derivative of mass with respect to time, is almost always zero. We rarely have an instant where the mass is changing. One example when we do have mass changing is rocket problems. And I'll do an example later on where we have a youth throwing bricks out of a wagon, and as he throws the bricks, he and the wagon and the bricks become a smaller massed unit. One thing to keep in mind as I'm talking about momentum is that it's a vector quantity. You cannot get rid of that concept. Momentum is a vector quantity. Alright, so if F is equal to dl dt, I can write dl equals F dt. I can integrate both sides. The left-hand side becomes a change in momentum. The right-hand side is just the integral of F dt. But a change in momentum is mass times velocity 2 minus mass times velocity 1. And this change in momentum will assume constant masses. This change in momentum is equal to impulse. And so you can see these last two lines. What I've done is I'm going to take this mass times velocity, which is negative, and I'm going to add it to both sides. That's going to bring it to the side of the equation with force. And so I get the initial momentum plus the integral of f dt equals the final momentum. So the change in momentum is the impulse. The change in momentum is also the integral of f dt. And so very simply, the impulse is either the integral of force with respect to time. If that's easy to do, you do it. Or it's the change in momentum. It will be both. But one of them might be easier to find than another. Now, a couple of interesting examples of the whole idea of impulse. Let's assume for a minute you jump off the table. Just before you hit the floor, you have some initial velocity. This is just previous to hitting the floor. A little bit later, after you've stricken the floor, your velocity is 0. It doesn't matter how you land, your velocity just before you hit the floor is some value v1, and your velocity after you've come to rest is 0. So what we're interested in is force times time. If you land and hold your knees locked, your time of impact with the floor will be very short. Now the right side of this equation is the same in both situations. But if I make the time of impact very short, in order to compensate, I must make the force of impact very large. Your whole body knows that. You've known that since childhood. And so what do? You don't land on the floor with your knees locked. You bend your knees and allow them to bend as you impact the floor. What that does is it gives you a large time of impact and therefore a small force of impact. The same thing can be seen with the invention of the airbag. The airbag was created so that the time of impact between the driver and the dashboard or steering wheel, time of impact would be increased, therefore making the force of impact smaller, and then the chances of injury lesser. when automobiles were first put out, the dashboards were made of metal. Knowing this, in the 60s, they began to pad the dashboards so that the time of impact between a passenger or driver's head in a head-on collision and the dashboard, that time of impact would be increased, thereby decreasing the force of impact. Another good example of FDT, you can think of a rifle versus a pistol. If I put the same kind of a bullet in a rifle and the same kind of a bullet in a pistol, the time over which the gases are exerting a force after you explode the gunpowder, the gases exert a force. In the rifle barrel, they exert a force over a long distance. In the pistol barrel, they exert a force over a short distance. Or, in the rifle barrel, they exert a force over a long time interval. In the pistol barrel, they exert a force over a short time interval. And so the muzzle velocity, which is here, the initial velocity being 0, the muzzle velocity will be large for a rifle, where the time over which the gas forces are exerted on the bullet is large, versus a pistol, where this velocity will be small because the time is small. Now, this equation looks very much like work and energy, and in fact it's very similar. 1/2 mass times speed squared. Notice this is velocity, that's a vector quantity. This is speed squared, that's a scalar quantity, plus an integral of f dot dr. Now notice this integral is an integral of force with respect to position. It's also a vector dot product, which means in the end it's a scalar quantity. That's going to equal 1/2 mass times a second speed squared. So work and energy yields scalar quantities, but impulse and momentum yields vector quantities. Very important distinction. So let's take a look at an example. In this example, I have a 4 kilogram particle, and it's being acted on by a force, and this force is a function of time. My mass is 4 kilograms. Force is a vector quantity, 4t minus 8 in the I direction, minus 2 in the j direction, and this will be expressed in newtons. The time is expressed in seconds. Let me just take a moment then to state this. 4t has units or dimension of newtons, and since t is in seconds, the 4 must be in newtons per second. The 8 and the 2 are newtons. So I could write this as 4 newtons per second t minus 8 newtons, that's all in the I hat direction, minus 2 newtons in the j hat direction. It's just another way of writing out that quantity. Alright, what we're interested in is finding the maximum speed between the 0 to 3 second interval, and we're given that the initial speed, the initial velocity, was equal to 0. So I can discover this by using impulse and momentum. So I have mass times the velocity 1, which that will be 0, plus the integral from 0 to some later time t of f dt. That's going to equal mass times velocity 2, vector quantity. All right, so the initial velocity, which is right here, that's equal to 0. And so what I'm ending up with is velocity 2 equals 1 over mass. Okay, I'm bringing the mass to the other side of the equation, times the integral from 0 to t, 4 newtons per second, t minus 8 newtons, that's in the I hat direction, minus 2 newtons in the j hat direction. And I'm going to integrate this with respect to time. That's going to give me 1 over mass. I get 2 newtons per second t squared, because the integral of t is t squared over 2. So the over 2 will cancel part of the 4. Minus 8t minus 8 newtons times t. This is in the I hat direction. Minus 2 newtons times t in the j hat direction. Now that's the velocity. Notice the question is, where is the speed maximum? So the speed is the magnitude of the velocity. How do you find the magnitude of a vector quantity? You take the I component and you square it, you take the j component and you square it, and you take the square root of all that. So this will be equal to 1 over mass. And I'm going to go ahead and drop my units now. I'm going to get 2t squared minus 8t. That's the x component, and I'm squaring that. Plus a negative 2t. That's the y component, and I'm squaring that. And I take the square root of all of that. So this is 1 over mass, 4t to the fourth, minus 32t cubed, plus 64t squared, plus 4t squared, all to the 1/2 power. That's my speed. So I'm going to take the derivative of speed with respect to time, and that's going to be 1 over mass, 1/2, 4t to the fourth, minus 32t squared, 32t cubed, plus 68t squared, all to the minus 1/2 power, times the derivative of what's inside, which is 16t cubed minus 96t squared plus 136t. And I want to maximize that, so we're setting this equal to 0. Well, when I do that, all that really matters is this part right here. Everything else over here is of no consequence because I can divide it all into the 0 and it goes away. So 16t cubed minus 96t squared plus 136t, I'm setting that equal to 0. Now I can pull an 8t out of there. So 8t pulled out leaves me a 2t squared minus 12t plus 17 equals 0. So one of my solutions is t is equal to 0. That comes from here. The other one will come from 2t squared minus 12t plus 17 equals 0. And I'll use the quadratic formula on that. So t is equal to 12 plus or minus the square root of 144 minus 4 times 2 times 17 all over 4. Now, of course, 17 times 8 is 136. So this is 12 plus or minus 144 minus 136 all over 4 equals 12 plus or minus the square root of 8 over 4, which is 6 plus or minus the square root of 2 over 2. And if I use the 6 plus the square root of 2, I'm going to get 3.707. That's larger than my time interval. So I want to use 6 minus the square root of 2 over 2. And that's 2.29 seconds, 2.293. And then I would go back into the original equation here and substitute that time in, and that would give me my speed.